Hi there, in this video we're going to go over another Fourier transform here. Now the function we're going to look at is this function here. It's f of t equals e to the at times u of t, where u of t is the step function, and we're interested in this for a less than 0. Okay, so there's a function that we're going to look at. Now what we're going to do is we're going to split this into even and odd components, and we're going to generate the Fourier transform of each of those, then add them together to get the final Fourier transform. And so let's get started, and you'll see the process here and the reasoning behind it. Okay, so let's say we're going to look at the even part of this function. Now, I don't know if I mentioned it before in the video on odd and even parts of functions, but I really should have. To generate the even part of this function, so f even part of time, what we do is we can take the function of time plus f of minus t divided by 2, and that will give us our even part, and we can get our odd part by taking f of t minus f of minus t all upon 2. Okay, and that will generate our odd part, and you'll see that here because that's what we're going to do here now. Okay, so what we do here is to generate the even part, we take f of t. Now f of t is just this here. Okay, so e to the t just looks like that. Okay, now we notice that that a has got to be less than 0, so you're going to end up with e to the minus t. Now e to the minus t just runs like that. Okay, now we're interested in e to the minus t, but this function here is the step function, and it only exists, it doesn't exist in the negative half here. Okay, so we're just going to end up with this function here, but only the positive part of it. So we'll end up with this thing, this function here. Okay, going down there like that. Okay, and that point there is a half. Okay, so this function here is a half e to the at times u of t. Okay, and then f of minus t, well, f of t, okay, so that again, e to the t would look like this. Okay, right, but now it's going to be e to the minus t. Okay, but what would happen here is you'll end up with e to the minus t, but our value of a is less than 0 as well, so it would be a minus t and a minus a, so the minus cancel out, you just end up with again a positive term, e to the at. So e to the at runs like this. Okay, now we're also going to have negative t in here, so it would be u of minus t. So we'll only be interested in the negative half of it here. Okay, we're not interested in the positive half here. So in effect, we're taking the step function and we've inverted the step function. Okay, so we're going to have something that runs down there like that. Okay, and this here is going to be our half, and it's going to be half e to the minus at times u of minus t. Okay, so that's one half of our function. Okay, now the other half of the function here will be the odd part. Okay, trying to keep this kind of straight. The odd part here. Now the odd part here, we're going to have gain f of t, so that's just going to be f of t e to the u to the t, which is the same as this one here. So we're going to have this one here, just the same as that. Okay, and again that's half e to the at u of t, and that point there's a half, and we're going to have minus f of minus t. Well, that's f of minus t there, but we're going to have the minus negative of it, which is equivalent to flipping it on the t-axis. So we're going to have this here flipped on the t-axis, which is just going to just going to look at that. Okay, so that there is our half e to the minus at, that's u of minus t, and it's a negative. Okay, so that's us split that function into those two. Now when we add them together, we'll get the final function. So this is a function of time. So that one plus that one, it's the same type of function. It runs, it's going to run like that. Okay, but now instead of the height being a half, it's going to be half plus a half, so the height will be 1. Now these are going to cancel out. That one is the negative of that one, so that cancels out. So that's the final function, which is e to the at times u of t. Now what I'll do is I'll rub this here out, okay, because I want to be able to draw the Fourier transform of it just opposite these. Okay, now I've already had a look in MATLAB and worked out what the Fourier transform is, and I'll show you the result of that. I'll just quickly draw one of them here. So what we have is, if I maybe draw it in, I'll just draw it in 2 dimensions here. Okay, so we have our frequency axis here, it's called j omega. Now, in fact, I'll call it omega, because it's just going to be purely real, isn't it? Okay, so that's a frequency axis omega, and it's a real even function of time. So from the previous videos that we watched, it should be a real even function of frequency. So the actual function, let's look something like that. Okay, now I'll go and bring it up just now. So I've done that forward transform of the even function. So we're going to look at this here. We'll have this here as our time domain function. This will be the forward transform. Okay, and so let me just go and fish this out here. Even part. Okay, right, let me just bring it up. Okay, so I think you can see that. Okay, so this here, it shows our function there. That's a function of time. Can click on it. That's it. Okay, so that's our function of time there. Okay, so that's the real even part of that function that we were looking at, and that's the Fourier transform of it there. Okay, and you notice it's a purely real Fourier transform. Now when I turn it around to the side, there shouldn't be any imaginary parts, but just because this function here, it doesn't tend off to infinity and minus infinity, it's clipped at minus 20 and plus 20. Okay, so you don't get it exact, but if I turn it to the sideways like that, okay, you will actually see all these blips. Okay, but all these blips, they're not really part of it. Okay, so there isn't actually any imaginary part to that function at all. Okay, it's a purely real function. Okay, now we'll go on and we'll have a look at the other part of it. So if I come back to our smooth draw here. Okay, now the Fourier transform of the odd part. Okay, so that's the even part there. This is the odd part. Okay, so the Fourier transform of the odd part, it turns out it looks like, I'll just draw it along this axis. So that's our omega axis, the g omega axis. Right, it's going to look like it looks something, if I can get it right. It's kind of like that. Okay. Okay, so the function looks something like that. Okay, so again, I'll show you that just now. So we're looking at this odd part here, the function, and that's the Fourier transform of it, and I put it in MATLAB there. So let's just bring it up, MATLAB. Okay, so there you can see that's the odd part of the function there. I run like that, so that's a function of time, and when I do the Fourier transform, I get this here, and that's the Fourier transform of it, just as you've seen in the drawing that I did there. Okay, now what I'll do is, if I bring back up smooth draw, then when I do the Fourier transform of this function, the Fourier transform of this function will just be the odd component to the function plus the even component. So the final version of this here, if I try and draw it in 3D now, I'll try my best to get it in 3D. So that's the imaginary axis, that's omega, and that's the real axis. Okay, so the real axis has got some function that looks like that. Okay, so I can just draw that, all these in, because it sits in that plane there. Okay, and the imaginary axis has got something that comes in and sits like that. Okay, and these are sitting in this opposite, this orthogonal plane here. Okay, so that there is should be the Fourier transform of this here. Now I've actually done the Fourier transform. You'll be able to see this now in MATLAB. Let's see if I bring it up. Oh, there we go. So that's it in MATLAB. So that there is our e to the at u of t. Okay, that's us added the even function, odd function together. We've got the final function there, and up here we've generated the Fourier transform. And now this should just be look like the even and odd functions. Okay, and if you were to turn it round like that, so now what we've got is we've got our imaginary axis here, we've got our real axis here, and we've got our omega axis here. Then if we turn it round like this to the real side, so there you go, that's the real part, that's the real part of our function. That's alright now. Okay, so that's the real part of our function, just as you'd seen, and you can find the imaginary part. So let's get this right here. Oh. Right, let's getting it there. That's it. This gets confusing actually, shuffle things about in 3D. So there you go, that's our purely imaginary part of that function there. Okay, just as we'd shown. Okay, that's the imaginary part of the function. It's good you can be able to see it actually in 3 dimensions. Okay, so there you go, that says in 3 dimensions there. Okay, so let's bring this back up to smooth draw back up. Let's go into smooth draw here. Okay, so that's us went through there, and we've shown that the Fourier transform is indeed this, and we're able to do this because of the linearity of the Fourier transform. Okay, so we're able to find the Fourier transform of the even part, the Fourier transform of the odd part, and then once we've found those, we can add them two together in the frequency domain, and we've got the final Fourier transform. We can do that because of the linearity of Fourier transform, and we'll go over that as one of the properties of the Fourier transform in the next videos. Okay, somewhere in the next couple of videos. So let's go, and I'm not going to go through this analytically or this one analytically because it just clutters the whole thing up. So we'll just go through this one here, and we'll just do the Fourier transform analytically of this, and we'll show that we get this here, and we can see what it is. Okay, so what we're looking for is f of j omega is going to equal what's the integral from minus infinity of our function. The function is e to the a t times u of t, and the Fourier transform will give us e to minus j omega t by dt. Right, now this, the limits here, u of t is only defined for t greater than or equal to 0. Okay, so that will just change the limit. So the limits of integration then will go from 0 to infinity of e now, and we'll join these exponents together. So you're going to have a minus j omega all times t by dt. Okay, so that's going to give us differentiate with respect to t, so you're going to have 1 upon A minus j omega, and that's going to be e minus j omega t. Okay, and that's all going to be from infinity to 0. Okay, so that's going to give us, well, the infinity part, that is going to give us 0. Okay, so we'll get 0 for the first bit, and then we'll get minus, and the 0 in for this will give us 1 for this part here, so it will be 1 upon a minus j omega. So the value over there will be equal to 1 upon j omega minus a. Okay, so that's a Fourier transform. So that's f of j omega equals 1 upon j omega minus a. Okay, so that there gives us that final MATLAB printout that we looked at. Okay, so that's our final Fourier transform. So that is the analytic description of our function, which is that function there. Okay, so that's the analytic description of that function. So 1 upon j omega minus a is that function there. Okay, now let's go back. We'll finish this off here. We'll just find out how we can find the magnitude and the phase of that. So what we can do is we could generate the magnitude. So we could, if I can finish it all properly, if I say f of j omega is going to have a real part of f of j omega, and we're going to have an imaginary part, okay, so say j imaginary part of j omega. Okay, now we can find that out from this if we multiply by the complex conjugates, 1 upon j omega minus a, right, and if we multiply that by minus j omega minus a upon minus j omega minus a. Now I'll do a video on the complex conjugate and why we do this and why we multiply this together in case you've not seen it. Okay, but I'll do that in the snippet section. So that there is going to equal minus j omega minus a all upon omega squared plus a squared. Okay, so that's going to equal, we split that into real and imaginary, so it's minus j omega upon omega squared plus a squared, and it's going to be minus a upon omega squared plus a squared. Okay, so these terms here would allow us to find out the real and imaginary parts of both of the function that we looked at. Okay, so what we could do is we can equate these. So what we're going to have is we're going to have the even part of time, right, which was our 1 upon 2 e to the at u of t plus 1 upon 2 e to the at a minus at, and that's the u minus t. Okay, now that there we gave us the real part, okay, a real even part of our j omega. Okay, so that part there would be this part here. Okay, I can't squeeze it in at the end there, so I'll put it at the bottom. So that would equal minus a upon omega squared plus a squared. Okay, so we're really saying that the even part of our function, the real even part of the function generates the real even part of our Fourier transform. Okay, and that's the real even part of the Fourier transform there. So that's that done analytically, and we can say that the odd part of t equals a half e to the at u of t minus a half e to the minus at, that's times u of, is that t minus t, u of minus t, isn't it? Okay, and that's going to give you the imaginary part, and it's an odd imaginary part of our function of j omega, and that's going to be this part here, so it's minus j upon omega squared plus a squared. Okay, and finally you can write that there as f of j omega equals a magnitude, a final magnitude. So if you were to add them together, or vectorially, this e to the j phi omega, you would get a real and imaginary part. Now the real part would be, the magnitude would be 1 upon root of omega squared plus a squared, and the phase of omega would equal inverse tan, and it would be omega upon a. Okay, so that there is generally the end point. Okay, so that's an analytic version of the description of our function of the Fourier transform of our original function here. Okay, so it's been quite useful because we've seen the idea of even and oddness, we've seen the linearity of the Fourier transform, okay, because we can have even and odd functions and we can add them up to get a final Fourier transform, and we've seen it, the analytic description of it, and we're able to look and see how the even function generates a real even function of frequency, and an odd function generates an imaginary odd function of frequency. And we found out what these values were, the a upon omega squared upon a squared, another one for the odd term is minus j upon omega squared plus a squared, and in the final version you can find out the magnitude and the phase of the f of j omega. Okay, now magnitude and phase, but again I'll go over that in the snippet section, okay, whenever I go over the complex conjugate stuff. Okay, so thanks for listening and goodbye.